Good morning, everyone. My name is Harold Bisibunghanay, and I'm here to talk about the plotting of a sinusoidal waveform, the average value and reference value of a sinusoidal current and voltage. So, in a sinusoidal waveform, just like this, it has many parts. This one waveform here it's one cycle. Then its half wave is called a one alternation. So each sinusoidal waveform takes a period of equivalent values. Here it is divided into 180 divisions, so namely 30, 60, 90, 120, 150, and 180. So for the whole cycle, it is divided into 360. Next is the average value of sinusoidal current and voltage. So for example, in this waveform, we can use the integral calculus to find the average value of this using its instantaneous currents, its waveform, and its periods. So for example, here, we have a divisions of I1, I2, I3, and I4. Then using integral calculus to find its average value, it is given in the form of 1 over t, integral of f function of t dt from the limits of 0 to t, where t is the time period of a periodic function. Next is the formulas. So here, I is equal to I max sine omega t and E is equal to E max sine omega t. While the average, the ratio of the average value and the maximum value of current is given in the form of I average is equal to 0.637 maximum current. Then the average of the maximum voltage and the average voltage is also given in the form of E average is equal to 0.637 maximum voltage. And the RMS value of a sinusoidal current and voltage is I RMS is equal to I max over the square root of 2. And the E RMS is equal to E max over square root of 2. So the RMS value, or the also known as the effective or instrumental value, so it's given in the form of F squared RMS equals 1 over t integral of F squared function of t dt from the limits of 0 to t. So extracting square roots in both sides, so F RMS is equal to square root of 1 over t integral of F squared t dt from the limits of 0 to t. So now we have given the ratio of the average value and the maximum value, which is I average equals 0.637 I max. Now, the question is how we derive this one. So from the given here, simple function I equals I max sine omega t, we can use this to find the remaining values and ratios. So a while ago, we have given the formula in finding the average value of an alternating or a sinusoidal current or voltage. It is given in the form of 1 over t integral of I dt from limits of 0 to t, where t is the periodic time in seconds or in radians. So our t here is equal to pi. That's why it takes the form of 1 over pi, the integral of I dt from the limits of 0 to pi, which is the half cycle of a sinusoidal wave or the first alternation. So we have an I here and we have a value for the I, which is the I max sine omega t. So we will substitute it. Then, since the maximum current is a constant term, we will extract it from the sign of the integral. So, it will become I max over pi integral of sine omega t dt from the limits of 0 to pi. Now, our integral here is integrable, so we will simplify it. So, the integral of sine omega t dt is equal to the negative cosine of omega t from the limits of 0 to pi. So, from here, the equivalent is negative cosine omega t plus c, but that c is a constant term which is neglected. So, here we can manipulate it, making it so here, we will simplify. So the negative cosine of 1 is 1. So making it plus 1. The negative cosine of 1. So 1 plus 1 is 2, making it 2 I max over pi. So our I average is equivalent to 2 I max over pi, or it is equal to 2 over pi I max. 2 over pi is equal to 0.637. So that is the derivation of this. So lately, we have discussed on the derivation of the ratio of the average value and the maximum value. Now let's have the derivation of the ratio of the effective value and the maximum value. So first is we have given the function of the instantaneous current, which is I equals I max sine omega t. Then lately also we have given the formula in finding the effective value, which is F RMS is equal to 1 over t integral of f squared t dt integral of from limits 0 to pi. So our t here is equal to pi, so we have to substitute t is equal to pi. Therefore, we have 1 over pi integral of I squared dt, where I is a differentiable function of the current from the limit 0 to pi. So we have I here, so we have to substitute the value of I. So here, I squared max sine squared omega t d omega t from the limits 0 to pi. Then since I maximum squared is constant term, we have to extract it from the integral sign, making it I squared maximum over pi times the integral of sine squared omega t d omega t from the limits 0 to pi. Since it is now integrable, we will now have to simplify it. So from our trigonometric identities, sine squared x is equal to 1 half minus 1 half cosine 2x. So this one is just equal to this one. They have a common of 1 half, so it is a constant, so we have to extract it, making it I squared maximum over 2 pi times the integral of 1 minus cosine 2 omega t times d omega t is equal to distribute. So integral of d omega t is double omega t minus the integral of negative cosine is still a negative sine omega t from the limits of 0 to pi. We have now this to manipulate. Omega t, substitute with pi minus sine omega t sine pi. So pi here is 180 degrees. So 180 times 2 is 360. So the sine of 360 degrees is 0. Leaving it with a pi. So our value, our equivalent for the I squared RMS is equal to I squared maximum over 2 pi times pi. Cancel pi, making it I squared RMS equals I squared max over 2. Extract square root to both sides. Now we have the final RMS value of I max over square root of 2. That equates here. Then same as with the voltage. So that's derivation on how to prove the ratio of the average value, maximum value, and the effective value. So now let's go to the form factor and peak factor. So form factor, in certain cases, it is convenient to have calculations at first upon the mean value of the EMF over half a period. Therefore, it becomes essential to have some means of connecting this mean value with the effective RMS value. The knowledge of form factor, which is defined as the ratio of effective value to the average mean value of periodic wave. So, form factor Kf is equal to the effective or the RMS value over the average value. So from our previous values, Kf equals our effective RMS, which is the I max over square root of 2, and our average value, which is equal to 0.637 I max. So by simplifying, I max here will be cancelled and the only numerical coefficients are left. Therefore, the answer is 1.11. Therefore, we can state that the form factor Kf is constant and is true to all. Now, let's go to the peak factor. Knowledge of peak factor of an alternating voltage is very essential in connection with determining the dielectric strength, since the dielectric stress developed in any insulating material and is proportional to the maximum value of the voltage applied to it. Peak, crest, or amplitude factor of a periodic wave is defined as the ratio of maximum or peak to the effective or RMS value of the wave. So here, peak factor Kp is being ratio with maximum value over the effective RMS. So from our previous values, peak factor Kp is equal to the maximum value over the effective or the RMS value, which is I max over square root of 2. From here, this is cancelable, leaving with only 1 over square root of 2, or is equal to square root of 2. Kp now is equal to square root of 2, or is equal to 1.414. So now let's take this as an example. The equation of an alternating current is I equals 42.42 sine 628t. So determine its maximum value frequency, RMS value, average value, and form factor. So, maximum value. So, this function given can be written in the form of I equals I max sine omega t, where the I max is the maximum value of current and omega is the frequency, omega t. So, therefore, to find the maximum value, we will just inspect here from the equation and observe what is the maximum value of current. Therefore, I max corresponds with the 42.42. Therefore, the maximum value of current is 42.42 amperes. Next, the frequency. So frequency is given in the form of omega equals 2 pi f. Omega here is the angular velocity and f is the frequency. F equals omega over 2 pi. So we have omega here and it corresponds in our equation as the 628. Therefore, our omega is 628 over 2 pi. Therefore, we will now have our frequency, which is equal approximately to 100 Hertz. Next is the RMS value. So to find the RMS value, we have a formula here given, which is IRMS equals the maximum value over square root of 2. And our maximum current, we obtained it in letter A. Therefore, we just substitute its value, 42.42 amperes over square root of 2. Now we have our RMS value of approximately 30 amperes. Now, in letter D is the find the average value. So from our previous formulas and equivalence, average value equates to the 0.637, the maximum value. Therefore, I average is equal to 0.637 maximum value. Our I maximum is the value of the answer of our letter A, which is 42.42 amperes. Now the answer is approximately 27 amperes. And lastly is the form factor. So form factor KF is given in the formula effective value over average value. So our effective value is the value of our answer in letter C, which is 30 amperes. And our average value is our answer in letter D, which is 27 amperes. Now our form factor is 1.11, and it satisfies in our derivation here, which is 1.11, and it is observable that all form factor and peak factor are constants in terms of sinusoidal equations. So now let's go to the other waveforms and their characteristics and values. So here we have two periodic functions that are not sinusoidal wave in form. So first is the triangular wave and the second is the square wave. So here in the triangular wave, unlike sinusoidal that it is its cycle is smooth. Here it has a pointy maximum value and pointy minimum value. So in finding the average value of a triangular wave, it is instantaneous current is given in the form of maximum current over pi, which is its half cycle period, times the theta, where theta is in between 0 to pi. So average value is given in the form of 1 over t integral of ft dt from limits of 0 to t, and our t here is equal to pi. Therefore, 1 over pi integral of I d theta from the limits of 0 to pi. So since we have a value of I here, we will just substitute its value. So here, I max over pi. Since this I max over pi is a constant term, we need to extract it from the integral sign, making it I max over pi squared, remaining integral of theta d theta from limits 0 to pi. So, from our past discussions of integral calculus, it takes the form of integral of u to the n. Its equivalent is equal to u to the n plus 1 over n plus 1 plus c. But in circuits 2, this c is being neglected. So here our u is theta and our n here is 1. So the integral of theta d theta is equal to theta squared over 2 from limits 0 to pi. Manipulating, making it pi squared over 2, cancel pi, and remaining is I max over 2. Therefore, the equivalent average value of a triangular wave is I max over 2. Next is finding the RMS value of a triangular wave. So, we recall that in finding the RMS value, it is equivalent to the square root of 1 over t integral of f squared function in t dt from the limits of 0 to pi. So, our t here is 5, so substitute. Then, our I here is equivalent to I max over pi theta. Substitute, and since I squared maximum over pi squared is a constant term, extract it from the integral sign, making it I squared maximum over pi cube, integral of theta squared d theta from the limits of 0 to pi. So, from here, it is now integrable. Its equivalent is equal to theta cube over 3 from the limits 0 to pi. So, manipulating, it makes pi cube over 3, cancel pi cube, the remaining is I squared over 3. And extracting square roots on both sides, it is equal to I maximum over square root of 3. In finding the form factor Kf, it is given in the ratio of the I RMS over the I average. Our value of I RMS is equal to I max over square root of 3 over I maximum over 2 equals 2 over square root of 3. Therefore, our form factor in a triangular wave is equivalent to 1.115. Next is peak factor. It is being given in the ratio of I maximum over the I RMS. So our I RMS is equal to I maximum over square root of 3. So cancel I max, making it square root of 3. So our peak factor for a triangular wave is equal to 1.732. And now let's go to the next waveform, which is the square wave. Square wave has a leading constant maximum value, then suddenly lags to the negative value and forms a periodic function. So, in finding the average value of a square wave, it is given in the instantaneous time is given in the form of I equals I maximum, since its maximum is constant and it lags to the next period. So, in finding the average, it is given in the form of 1 over pi integral of I d theta from the limits of 0 to pi. So So substitute the value for the I, which is I max. Then since I max is a constant term, we need to extract it from the integral sign, making it I maximum over pi times the integral of d theta from the limits of 0 to pi, which is theta. Then manipulating theta minus 0, which is theta, cancel the pi, cancel the pi, making it I maximum. So our average value is equal to the maximum value, which can be seen here in the graph. Next, in finding the RMS value, it is given in the form of square root of 1 over pi, integral of I squared d theta from the limits of 0 to pi. So, substituting the value of I, which is I max, making it I squared maximum. Then, since it is a constant term, we need to extract it from the integral sign, making it square root of I squared maximum over pi times the integral of d theta, which is theta from the limit 0 to pi. Manipulating, making it pi minus 0, pi, cancel pi, and remaining is the square root of I squared maximum, which is I max. Therefore, we can conclude that the I average and the I RMS is equal to the maximum value. Now, in finding the form factor of a square wave, it is given in the ratio of I RMS over the average value, where our value for the I RMS is equal to I maximum over the value of our average value, which is I maximum, cancel, making it 1. Next is, lastly, is the peak factor of a square wave, which is given in the ratio of I maximum over I RMS, where our I RMS is equal to our I maximum and cancel equals 1. So therefore, the form factor and peak factor of a square wave is 1, and it is definitely, we can see in a graph which is like a DC but lags every periodically.